Good morning. Today I'm going to talk about differentiability. And you won't have to spell that very often, which is good because it's an ugly word. Differentiability. Differentiability means that a function is able to have its derivative taken. It also means that the derivative of a function exists. If a function is differentiable, then it means that its derivative at a certain place does exist. We're going to tie all this into limits and continuity towards maybe the middle of the lesson here. Let's just look at a few examples first, though, to kind of understand what the concept is telling us. Use the grid provided. Graph the function of f of x equals absolute value of x minus 3. Okay, that is going to look like the parent function y equals the absolute value of x, except it is moved over 3 spaces. Come on, straight line. There we go. That was not a good example of a straight line. Let's look at the questions. What is f prime of x as x approaches 3 from the left? F prime of x is our shortcut notation for the derivative, and the derivative is equal to the slope of the tangent line. So what is the slope of the tangent line through here? That's a better straight line a little bit. Well, the slope of the tangent line is just going to be the same thing as the slope of that line. It is -1. What is f prime of x as x approaches 3 from the right? So what is this? Oh, goodness gracious. Time out. Much better. Okay. So what is the slope on this side as x approaches 3 from the right? Well, that happens to be a +1. Is f continuous at x equals 3? Yes, it is. Let's see. We could just come down here. That is defined. And then we would go back up. You could use the old-fashioned, yes, I can do this without picking up my pencil. You can use your limit definitions. It's definitely continuous, or you can just look at it. It's definitely continuous at x equals 3. Now, the question is it differentiable at x equals 3? And the answer is going to be no. We're going to call this place here a corner or a point or a sharp place, or you call it many different things. It really doesn't matter what you call it, as long as you understand this. Look at what's happening to the derivative. As you approach from the negative side and you get closer and closer to x equals 3, the derivative is staying, right, exactly at a -1. The derivative all through here is -1. And then all of a sudden, just at a brief, teeny tiny split second of time, the derivative jumps and is suddenly a +1. Well, we can't have those kinds of jumps. We can't have those sharp turns, those roller coaster points where you're riding along a roller coaster and you just, if we're imagining riding down here on a roller coaster and you're suddenly needing to turn up here, well, the roller coaster would just hit. It wouldn't actually turn and go up. We need a smooth curve in order for something to be differentiable. So, to answer our question, is f differentiable at x equals 3? No, it is not, because there's a sharp corner there, and because the derivative on the two sides is so different that there's no smooth path to get from one derivative to the other. Let's look at the next one. Graph f of x equals x to the 2/3 power. That looks like this. Pretty good. Something like that. Describe the derivative of f of x as x approaches 0 from the left and the right. Okay, so as x approaches 0 from the left, what is happening to the derivative? Remember, the derivative is the slope of the tangent line. So let's draw some tangent lines. Here's one tangent line. Here's another tangent line. Here's another tangent line. What are these tangent lines? What is the slope of these tangent lines approaching? Well, what did it start out at? Is it started off as a fairly um, close to zero negative number, right? Maybe that tangent line here was, I don't know, negative 1 over 10 or something. I don't know what that would have been. And then it grew, and it is approaching, what is it approaching? It's approaching a very large number, and it's going from 0, and it's in the negative, so it's starting kind of at a 0 and then going through all the negatives, and it's approaching a bigger number. So really, if you think about it, it's approaching negative infinity. So I'm going to say f prime of x is approaching negative infinity. Now the next side, let's see if I can change colors here. What about as x approaches 0 from the right? Well, my tangent lines are doing something like this. Do you agree? If I were to zoom in right there on that point right there, if I had something like this, and I zoomed in on it and zoomed in and zoomed in and zoomed in, I would have all these infinite tangent lines that are slowly, not slowly, quickly, becoming almost a vertical tangent line. So let's go back to here. So as x approaches 0 from the right, what is happening? Well, I have a positive, these are all positive slopes. So it is approaching a positive infinity. All right, now let's look at the next part. Suppose you found f prime of x equals 2 over 3 times the cubed root of x. That actually is the derivative of this. If f of x equals 2, or sorry, if f of x equals x to the 2/3 power, then f prime of x equals 2 over 3 to the cubed root of x. Now, I wouldn't ask you to do that with your limit definition, but as of, I don't know, Thursday, we'll be doing this in a different way, and you'll be able to do something like this pretty quickly. So let's look. What is the value of the derivative when x equals 0? Well, if you're telling me that the derivative is equal to 2 over 3 times the cubed root of x, and you want to know what the derivative is when x equals 0, well, you just simply plug in 0. What happens when you plug in 0 here? You get 0 in the denominator. What does that tell you? That tells you that the derivative at x equals 0 does not exist, or is undefined. Undefined. Oh, and by the way, we call this right here, we don't call it, it's not a point or a corner. It is kind of a point, but it has a name in calculus. It's called a cusp. You'll just recognize that anywhere there's a sharp, pointy place, whether it's a cusp or a corner or a, I don't know, sharp angle, those are places where the derivative does not exist. Let's look at the next one. Graph f of x equals the cubed root of x. Well, I'm going to try to graph this. It is the one, it does something like, oh goodness, I tried. Something like that. Okay, so let's look at what's happening with the derivative. Describe the derivative of f of x as x approaches 0 from the left and the right. Okay, so the derivative, if I make some lines again, the derivative, help if it was actually touching the graph, is coming in and doing this. The derivative is equal to the slope of the tangent line, so I'm drawing some tangent lines here. Kind of messy. But what happens to the slope of the tangent line as we get closer and closer and closer and closer to 0? Do you recognize that the tangent line is approaching a vertical tangent line? Do you recognize that hopefully at that place when you have a vertical tangent line, it does not exist? Well, let's see, how would I write that right now? I would write as x approaches 0, and this is from the right or the left, the derivative is approaching infinity. It's a vertical tangent line. Suppose you found f prime of x equals 1 over 3 times cube root of x squared. So again, we will have a method for doing this very soon. But for now, we're just told, here's the derivative. The derivative is 1 over 3 times the cubed root of x squared. What is the value of the derivative when x equals 0? Well, once again, we have 0 in the denominator. So it is an undefined derivative. F prime of 0 is undefined at x equals 0. And that's because we have a vertical tangent line. Which is like this. And that means no slope. If you have no slope or a vertical tangent line, then your derivative at that place is undefined. Your function is not differentiable at that location. So the graph of f of x equals the cubed root of x is not differentiable at x equals 0. All right, talk about a little geometry here. Not geometry with shapes, but this is more like the proof stuff of geometry. In all three of the previous examples, excuse me, I'm yawning, the functions were continuous, but failed to be differentiable at certain points. What were those three places? First we had a corner, then we had a cusp, then we had a vertical tangent line. So anywhere you have a corner or a cusp or a vertical tangent line, the function is not differentiable. So those were all three continuous on those places, weren't they? Remember the corner, that was continuous. The cusp, it wasn't very pretty, but it was continuous. And the vertical tangent line, the graph with the vertical tangent line right here, that is a perfectly continuous function, but is it a 100% differentiable function? No, it is not. So what we need to get at here is this statement right here. Differentiability implies continuity. If a function is differentiable at some point, then it is also continuous at some point. But very important, it does not work the other way around. Just because a function is continuous does not guarantee that the function is differentiable. So continuity does not guarantee differentiability, but differentiability does guarantee continuity. Okay, let's look at this. For the logical statement, if A, then B, the converse is written, if B, then A. Maybe you remember this from geometry, maybe you don't. The converse of the statement in the box is not true. What is it? Well, even though it's not true, we're going to write it down just to remember converses and such. It would say, if f is continuous, I want to say at x equals c, then f is differentiable at x equals c. But hopefully you realize now that's not true. Just because a function is continuous at a point does not mean it's differentiable at a point. So I'll put a big cross through that. Let's look at the next one, example 5. The contrapositive of any statement is logically equivalent to the original statement. The contrapositive, if you remember from geometry, is kind of like the negation of the opposite of the statement. It's like a double negative, okay? You're switching the statement around and you're saying that it's not true. So what would we do here? For the logical statement, if A, then B, the contrapositive is written, if not B, then not A. Does that make sense? If A, then B turns into if not B, then not A. What is the contrapositive to the statement in the box? Well, it would be, let's see, if f is not continuous at x equals c, then f is not differentiable at x equals c. Is that true? Yes, that is true. That is a true statement. If the function is not continuous, then it is definitely not differentiable. You can kind of stop there. If it is continuous, it may or may not be differentiable. You can't guarantee that. Okay, let's look at the next page. If you're given that f is differentiable at x equals 2, then explain why each statement below is true. Well, before we even look at the statements, let's look at what this says right here. If you're told that f is differentiable at x equals 2, if it is differentiable, then we know that it is also continuous. So let's see, f is differentiable, so f is continuous. Well, if a function is continuous, then we know that the limit exists at that location. F at x equals 2, limit exists. And in order for the limit to exist at x equals 2, or excuse me, for the function to be continuous at x equals 2, two things have to happen, right? The limit has to exist and f at 2 must exist. Remember, because it has to actually equal the limit. Okay, so let's see what else we can figure out here. Okay, the limit as x approaches 2 of f of x exists. The limit as x approaches 2 of f of x exists. Would this have to be true if the function is differentiable at x equals 2? Yes, it is true. Check. What about the limit as h approaches 0 of f of 2 plus h minus f of 2 over h? Okay, do you recognize this as the definition of derivative? Do you recognize this as the slope of the tangent line? Hopefully so. So if the function is differentiable, then of course the derivative exists. Yes, at this point, at x equals 2. All right, what about the next one? F of 2 exists. Well, yes, that has to be true, because if the function is differentiable, then the function is continuous. If the function is continuous, then the limit from the right and the left have to equal the function at that point. So of course the function at that point exists. Check. Now the last one, that's just the alternative definition of derivative at this point. So again, yes, this has to exist. Maybe this makes sense. Maybe you need to go back and listen to it again. Maybe you need to take a second and on a separate piece of paper somewhere or on your notes, you need to kind of write out your thoughts about differentiability, continuity, and limits. It's very important that you understand the link between differentiability, continuity, and limits. This is something we continue talking about throughout the year, and it's just a big concept in calculus. All right, let's look at the next one. If f is a function such that the limit as x approaches negative 3 of f of x minus f of negative 3 over x plus 3 equals 2, which of the following must be true? This is a very, very typical multiple choice type AP calculus exam question. I'm not saying for my exams, although I'm sure there'll be something like this on our test. I'm talking about for the AP exam at the end of the year. Hopefully you're planning on taking that. This is a very typical question. You definitely see a multiple choice question like this, I would say, and there are also probably a free response question that uses this information. It won't be this simple, but it will use these types of properties to continue. You'll have to understand this in order to continue the problem. All right, let's look at what we need to say here. All right, we're looking at what must be true. A, the limit of f of x as x approaches negative 3 does not exist. Well, what does this tell us right here? This up here tells us that the slope of the tangent line at negative 3 is equal to 2. What else does that tell us? That also tells us that the derivative of f of x at x equals negative 3 is 2. What does that mean? That means f prime at negative 3 is equal to 2. I'm really just saying the same thing over and over and over again, but I'm using different words. I hope that makes sense to you. Okay, so go back here. The limit of f of x as x approaches negative 3 does not exist. Well, if the function is differentiable, and if it does exist, then it is continuous. If it's continuous, then the limit definitely exists. So this is not true. What about B? F is not defined at x equals negative 3. Well, again, if the function is differentiable, which it is because they tell us, then that means it's continuous. If the function is continuous at x equals negative 3, then the limit from the right and the left has to equal the function value at that point. So the function value at that point has to exist. So this is definitely not true. All right, C. The derivative of f at x equals negative 3 is 2. That is exactly what I just wrote here. That is exactly what you are told here. So yes, that statement is 100% true based on the information we were given. How about part D? F is continuous at x equals 2. Now, what is x equals 2? What is 2? 2 is the slope. 2 is the slope. Do we have any idea what's going on at x equals 2? No, we don't. We have no idea. There's no substituting in up here in the original equation for x equals 2. The x value that we're concerned with up here is negative 3. 2 just happens to be the slope. This is a bit of a trick, okay? Is f continuous at x equals 2? I don't know. It might be, but we don't have enough information to say yes or no. So what we would say, I suppose, is maybe. Maybe. That's not how you spell maybe. There we go. Maybe. But if you were going to answer the question, which following must be true, then this doesn't necessarily have to be true. It could be true, but we don't know. All right, now look at E. F of negative 3 equals 2. That is not the derivative at negative 3 equals 2. That's the original function value at negative 3. There is no information through all of this that tells me what the function value when x equals negative 3 is. I have no idea. So again, this is one of those that might be true, it might not, I don't know, but if I have to say for sure whether it's true, I'm going to say no. The only thing I can say for sure is true is C. Okay, I am going to wait on this. The rest of the lesson here is talking about using a calculator to find a derivative, and I would really rather do that in class when I know that we all have a calculator in front of us. So we're going to look at that. Also, our calculators make it so simple. It's, I don't know, maybe a 5-minute lesson tops. It's just ridiculously easy to do on the CAS calculators. It is something that the AP test requires you know how to do. There are some multiple choice questions where you have a calculator at your disposal that you need to know how to just very quickly punch in a derivative and get a derivative off your calculator. So we're going to look at that. We're going to look at it analytically with the just punching in with numbers, and we're going to look at finding the derivative graphically on your calculators. Okay, but that's it for now. Bye. Oh, your homework is, let's see, your homework is the 3.2 worksheet. You don't have to do that right now. If you want to get started on it, that's great. I shouldn't have said it's homework. That's more going to be our classwork. I suppose your homework was to watch this video and to do anything from the 3.1 worksheet that we have not completed in class. Okay, please, when we're in class, just a side note here, you guys are the ones that voted for us to do a flipped classroom where I'm trying to teach before we come to class on these videos, and then we're going to come into class and work problems. It is your responsibility to ask questions in class. I'm walking around, and trying to see who knows what, but it really, if you need to see a problem, if you need me to help you just personally with a problem, or if you want to put one on the board, that really, I cannot read your mind. I need you to answer me I need you to ask questions. What am I trying to say here? You know what I'm trying to say. So speak up. Don't be shy. Ask questions. If you're not understanding this, I guarantee you, you're not the only person in the room that is a little bit confused. So let's ask more questions. I guess that's all I have to say now. I hope that you also come into class with your notes filled out, because that shows me that you have watched the videos. Okay, that's all. I'm going to stop talking now. Bye-bye.